the automatic recognition of solar radio bursts and NenuFAR observations, as Cameron said. Oh dear, which one of these does what? Okay, a quick outline of what I want to tell you all about. Solar radio bursts. We've heard and seen a huge amount of solar imaging and different types of solar data this week so far, but not so much in the radio, and it's close to my heart, so I'm going to spend a bit of time there. NenuFAR, the telescope that I'll be using to look at all these. Semantic segmentation, one of the machine learning technique I'm using to try and figure out when these things happen. And then I'll go through bits of how I did it, what it looked like, and what I want to do next. So to start off, there are 5 sort of classical types of solar radio bursts. They're all, there is a laser pointer on this, but I'm sure I'll push the wrong, yeah. Never mind. There are 5 different classical types where each of are sort of classified by their drift rates. So you'll have, brilliant, thank you. You have the type 3s, which are probably the shortest lived ones. They go from hundreds of megahertz in frequency, and they last very, very short time span, maybe 1 minute. Type 2, these longer sort of ones, these are indicative of shocks in the corona. And then you have types 1, 3, or 1, 4, 5, and things. They all have their own different meaning. I focus mostly on type 1, or type 3s and type 2. So I'll sort of stick to that. They can exhibit fine scale structure as well. So not only do you have this sort of long, smooth drifting thing, you can actually have them in smaller chunks, and they have very, very intricate details once you zoom in the frequency and time domain. And this is sort of a typical classification problem. We have some data, and we have shapes in it. We want to find out what they are automatically without spending too much time on it. NenuFAR is the the new extension to LOFAR in NonSay. So it's basically a whole bunch of antennas, the LWA style antenna for anybody who's familiar with that, but it's an add-on to the existing LOFAR station in Nancy in France, and has become a sort of superstation in its own right. There are almost 2,000 of these sort of antennas dotted all around a large area, giving you a high spatial resolution for imaging, which is great, but in particular for what I want to talk about, great frequency and time resolution. So 3 kilohertz in frequency and about 1 millisecond in time, and they span 10 to 85 megahertz. So the low parts, as low as you can go basically for radio astronomy from Earth. And this thing generates data at huge rates, sort of 3-point-something gigabits per second, which really, really adds up when you start looking at the sun for 8 hours a day, if you can get it. A few examples of what NenuFAR sees. So here's what we have, what I call it, or what is called a type 2 burst. You can see we have a slow drifting thing over the course of maybe 20, almost 30 minutes here, spanning almost the entire frequency scale as well. So from 80 all the way down to 10 megahertz in the noise here. And you can see within that as well, there's smaller patches of brightness and even, again, fainter things here. So there's lots of intricate details as well. We also have things like a type 3b burst, so a subset of some other type 3 burst. And again, now we're at a much narrower frequency span, but look, notice here we're only spanning about 8 seconds. And these things are very, very narrow and very, very fast and very rapid. And these things can hopefully tell us all about Langmuir waves in the solar corona, and lots of exciting things there too. And then finally, we have stuff that I've never seen before and just doesn't have really a classification. So if anybody knows what this is, by all means, let me know. But I've never seen anything like it, and I haven't seen anything since. So, but oops, yeah. Again, though, very, very short-lived, sort of bursty things, and a very narrow frequency range as well. So we want to be able to try and know, or want to try and figure out what these sorts of things are and why do they have such fine scale structure in frequency and time. So as I've just shown, solar radio data is very diverse. There's all sorts of different things going on, even within our broad classifications. The data files are large. I mentioned the data rate was something like 3.2 gigabits per second, but really what it adds up to is that over the course of maybe an hour or 2 hours observations, you're hitting 100 gigabytes of data. And you can't keep that forever, certainly not in its raw state, or at least not with the limited funding that may or may not come with multi-million euro telescopes. So really the goal here is to try and automatically determine, while the telescope is recording, when do we need this fine scale structure? So for something like, I don't know, for something like the things I'm showing here, you definitely want the frequency resolution that this thing affords you. But maybe for the type 2, you see that the time, it spans a much longer time. Maybe you're not so interested in the time, so you can afford to rebin or integrate in time a little bit. So this is sort of the real question, and then can we do this automatically using machine learning? Jeremiah spoke yesterday, or he mentioned yesterday about some of his previous work where he's actually successfully applied YOLO to get bounding boxes around type 3s, which is great, but it's not quite what I'm hoping to do with this work. The bounding boxes give you a good location of where the type 3s are, but I wanted a more specific sort of location, not because these things these aren't boxes themselves, they have this drift structure inherent to them, so hopefully there's a better way of trying to locate them in a dynamic spectrum. That's what we call these things. And this is where semantic segmentation comes into it. So I'm sure some of you are familiar with the concept at least, but the basic point is we have an image such as this streetscape here, and in this image you want to classify every single pixel. So you want to know where are the cars, where's the road, where's the footpath, where are the walls, and you get this sort of mask thing here, and a precise location of every single pixel or every single object in the image in the first place. The way I'm implementing this is using UNet, quite well known for this sort of thing. Basically, you take your input image, pass it through a whole bunch of layers, making it smaller and smaller and smaller until you get to this encoding layer. And then you bring it all the way back up, and you have an output segmentation map. And so the way the training works is you compare this output segmentation map with your ground truth segmentation map, run it through the whole malarkey, you know yourselves, and not hope for the best, but hope for good results. Before we start doing that, though, we need to get our data set ready, and that requires labels. As I've said, solar radio data is incredibly diverse. So diverse, in fact, that for me to do it on my own is just impractical. So out of sort of this, the solution I came up with was start something simple and improve upon it. So rather than spending hours of my life drawing little things, and this is a type 3, this is a type 2, this is something I've never seen before, but I'll call it a Z or whatever, I have just said anything above some sort of threshold is a radio burst, anything below some sort of threshold is not a radio burst. And we'll see how we go from there. So what I'm showing here in the blue is what's called a cumulative sum slope of a particular frequency range that we saw earlier. And a cumulative sum slope, it's essentially just a running average of your data. And what I'm showing here in this gray line is a mean threshold. So the mean of this cumulative sum slope, anything above that, all this stuff, this is burst, everything down here is not burst. And as you can see, that's not very good because we have some spike things here that are probably radio bursts. In fact, this one peaks up over it, but the rest not so much. So I've also implemented a second threshold. This is this orange line here. And the orange line is a Savitsky-Golay filter applied to the cumulative sum slope. So we're smoothing a running average thing, and anything above that is now a burst. And the effects of this are quite dramatic. So if I show here, this is the same type 2 burst I showed earlier. This is using the mean threshold. So you can see it really does get all this type 2, which is great for a very silly, very, very simplistic, if it's brighter than this level, make it a burst. But it works. That's great. But you can also notice that, let's say, this type 3 here, it picks out the bottom half and it gets a tiny little bit at the top, but it's missing the things in the middle. And there's quite a few weaker type 3s in here that don't get covered all the way. So there are some problems with the very, very simple threshold. Applying the smoothed threshold now, however, that changes things dramatically. We see hundreds upon hundreds upon hundreds of type 3 bursts that are lying hidden in the background, not in the background, but the color scaling on this isn't probably the best to see them above, but they are there. I've zoomed in and checked them all. But on the flip side, what was once our lovely bright chunk of type 2 is now this sort of weird mess of smaller bits. Probably because, as you can see here, when we go up here, it's getting the local peaks, so to say, rather than the overall picture. So I was quite happy with this because type 3s are sort of close to my heart. Type 3s happen incredibly more frequently than type 2. So I said, look, let's go with this. We have something. I have, what, 200 or so hours worth of recording. Chop every single day that I have into about a minute in time and some frequency range that I can't exactly remember, but tile it all up, shuffle it all appropriately, I hope, and put it into the algorithm and see what we get out. So here is just a terrible plot, which is a screen grab from TensorBoard. But what I'm trying to show here is that these ones up on the top, this is the validation loss. This is actually a lot of plots all on top of each other, but it is the training loss. So what I've done is a k-fold cross split, and just trying to see that depending on how I shuffle the data, do I get the same sort of results? I do, so I'm happy enough that I'm taking an appropriate training test split. And yeah, importantly, it also decreases as the number of epochs increases. Maybe not particularly quickly, but it does decrease, so we're going in the right direction at the very least. Here are some more plots. I think, yeah, the most boring part of machine learning is showing the the loss function plots, but they are quite important. Thank you. I have, what do I want to say here? So the best way I can think of sort of quantifying the results from segmentation is this IOU score, intersection over union. It's basically trying to get the overlap of your real input and your predicted input, or outputs rather, and seeing how they compare. And for both output masks that I have, that I didn't mention until now, but I have 2 masks, it performs quite well. I mean, upwards of above 75% maybe for both in the validation set, which is quite good. It's not perfect, but we've seen that the input isn't quite perfect either, so there's a bit of that. And then the F1 score, again, increasing as the epochs go along. This red line here marks the point where I stop training at a certain level, and then just decrease the training what's that called? Learning rate. Decrease the learning rate and unfreeze some of the frozen encoder parts. Here's what, I'm going to skip these because I have a movie and I prefer the movie. What I'm showing here is across an entire day. The middle one, here's the ground truth mask for the two output masks that I have. Anything in yellow is a burst, or in here anyway, and then down here it's whatever. And the predicted mask here on the right. And we can see, maybe it's moving too quickly, and apologies for that, but we can see that it is picking up quite a lot. I want to wait a little bit for the type 2 to kick in, which should be about now. No, okay, well, around 12 o'clock, but we can see this moving on. You'll notice that the white contours here are just this. Here's the type 2, and you can see it picks up a lot of the small stuff quite well. There's a band up there that was very uncertain, and maybe I'll get onto that if I have a bit of time. But you can see there's these contours, which are just the contours of the predicted mask mapped over here. Very noisy in this one down here, probably as a result of the mask in the first place.
Sorry, what's the difference between the top and the bottom?
Yes,
rows?
sorry about that. The top here is Stokes' I. It's the intensity in Stokes' I parameters, and the bottom here is the absolute value of Stokes V divided by Stokes I. So it's a proxy for polarization of the waves, or of the radio. Yeah, this is just a plot of the IOU across that movie, so we see that it works quite well across the movie. Here's where the type 2 comes in, and you can see the results are not as good, which again is probably indicative of the fact that we don't have a lot of type 2s to train on in the first place. This is a percentage of how much is masked. Maybe this can be used for actually making decisions on what we want to do with the data once we have it working. Here's some means, a nice histogram of the IOU. So better than not, but not perfect. And again, for the Stokes V parameter, slightly worse than Stokes I, but still more better than not, which is the right direction. And then finally, I had the great idea of, wait a second, why do I need to have only one threshold? Why not I just use both at the same time? And that is what I did, and the results came in last night, so frantically putting this together. More screenshots from TensorBoard. We can see that the epoch loss, it's going down, it's noisy. I mean, literally, this came in last night, so I haven't had a huge amount of time to study it, but in the right direction, which is good. Now the individual IOUs for the Stokes I, quite good again over 75%. Not as good for the Stokes V, which is a sort of a common trend. But again, I think it's probably because the silly masking threshold I'm using is not quite as appropriate in the polarization data. So to some possible next steps, need to work on improving this IOU for both classes. Need to start making decisions based on the outputs of this, because that is the whole point here. From these masks that we get out, can we say, okay, well, there's this percentage of small things, so save the data at a very high resolution, otherwise don't worry about it. And then how to actually do this properly. Can we get hundreds of thousands of people to look at radio bursts for ages on Zooniverse or something like that? I think that is an ordeal in and of itself, but worth looking into. So to conclude, thank you all for your time. 200 hours of NenuFAR solar radio data observations in 2022 went into sort of training this data set, which is about 14 terabytes, if anybody's wondering. I trained the UNet to locate the times and frequencies of solar radio bursts. And success, sort of, depending on your level of success. It does detect what I have told it to in a way, but what I've told it to detect is just a very simple threshold. So more improvement to be done for sure, but I think we're really, yeah, very promising so far. And then, yeah, I mentioned it a few times, that the Stokes I emission versus the Stokes V emission, they're not perfectly at the same level, but hopefully we'll get there. So again, thank you very much for your time, and any questions, I'm happy to take them.
Thank you. Okay, I'll take the opportunity to ask a couple of questions in the beginning. Very interesting presentation. Can you briefly explain how you're using both thresholds at the same time for this last part?
Yep.
And also, how much retraining would be necessary to apply this to other observations, say LOFAR, for example, or something else?
So this is actually an interesting point. How do I do both at the same time? If I go back, so I have this is from the threshold, and I take that and I just put it to one side, and this is from the smooth threshold, I take that, and then just a binary AND, or binary OR to get both. I've not entirely sure of how to deal with when you have something that is in both. So something that is classified by both, like let's say for these smaller things within the type 2, this would be part of the small scale structure in the type 2, but it's also part of the broader scale thing. And how, again, when you have stuff detected in the polarization, when something is detected in both polarization and Stokes I, how to deal with that. I think the multi-label, multi-classification sort of stuff, not entirely sure how to deal with. But to go to your second question, how to do something like this for LOFAR, I think it's quite similar. I mean, for the LBAs and LOFAR, it's the same frequency range. And the input here, I've normalized out the bandpass. So as long as you can normalize the bandpass for LOFAR, I think it's the same
it's just
process.
An array,
yeah.
a 2D array, basically.
Yeah, yeah, I think so. And yeah, chopping up your data appropriately.
Okay.
Whatever that might mean.
Andre?
Yes, thank you very much. Very interesting. So I've two comments. So the first image, the unclassified, aren't these spikes, millisecond radio spikes? I was wondering.
So whenever I hear the term spikes, I always think of sort of gigahertz or like submillimeter, but possibly. I mean, yeah.
Yes, your lower frequencies.
Yeah.
Absolutely. Yeah. Okay. Yeah. And I have a comment. Okay, so maybe also it's maybe not totally the same frequency range, but for eCallisto we have a list of labeled data.
I have seen this actually.
You've seen this.
Yeah.
Okay.
Yes, right. And it's quite extensive. And yeah, I think for the type 3s or for the type 2s, I think it would be perfect. But for stuff like type 3s, you have like very bright ones, but not necessarily all the tiny small ones that you can see. But yeah, it would be a great starting point.
And the question was about the UNet. So for the UNet, you must have some kind of maybe I missed it, but so you have kind of a standard input size, right? But you have your events are very different time scales.
Yes.
So you have type 3s are very small, very short-lived, and the type 2s very long. So how do you manage to give that to the UNet in a somehow standard?
Yeah,
form?
I don't. Is the short answer. The way I do it, everything that goes into UNet is the same size, regardless if it's type 2 or type 3. You're dead right, though, that these things are on different timescales, and it probably would be appropriate to have stuff that is type 2 be bigger going into UNet to get more of the idea. I've tried doing everything at a bigger scale, and I ran out of memory a lot. But yeah, I think maybe downsampling the type 2s and then making them bigger, something like that, yes. That also does still involve knowing when the type 2s are, but I mean, we're going to have to do that eventually. Let me see where I have UNet. Anyway, yeah, but the short answer is everything that goes into the UNet I'm running, it's 256, well, pixels, but it's actually yeah, in data space. So I think it's 0.25 seconds in the time direction and 8 times 3,000 kilohertz in the frequency direction, because that's how I divided it, but I can't remember the actual number.
Thank you. Thank you.
No worries.
Thank you. More questions? All right. Robert, then Felix.
Thank you for the talk. So I have a question about how you prepare basically your ground truth. So you're using this thresholding method to create basically the training labels, which you then also consider for ground truth. So what is the real advantage of using the units then? Because you already have kind of the threshold, which is the thresholding method, which is kind of simple as a target. So how are the results that you get from unit different from just a simple thresholding method then? Yeah, that's like a very valid point. Like, if I already have all these things, why bother doing UNet at all? I think there is, let me see. Maybe these aren't the best to show it, but there have been cases where the output from UNet does actually cover stuff that doesn't get picked up by the ground truth, if you want to call it that. I don't think anything in particular here shows that. Maybe here actually, so you can see, what are we going for here? This sort of, yeah, that's not a great example either. Okay, I should have put more thought into the ones I showed here, but there are cases where the output of UNet does pick up stuff that isn't determined by the threshold. But also, I think, for me, I just need something to get me started, and I don't want to be sitting labeling things, so it was better than nothing, and yeah, I fully understand that it's limited, but and also I think there's more sort of scope to grow using UNet than just using the thresholding and then tweaking with it, and somewhat arbitrarily, I would say. But yeah, a really valid point. Okay, thank you.
Yeah, this is also very important for very low flux bursts, I think. Felix?
Okay, thank you very much for your presentation, but I just want to understand if your UNet take images as input, and also if you perform some sort of, let's say, background cancellation to mitigate radio frequency interferences, because I saw that most of your spectrum were affected by RFIs. Thank you.
Yeah, so it doesn't take images, like it's not a PNG that goes in, it's the actual data itself. In whatever raw binary format that is. As for the RFI, so I didn't mention, but once I do this, I do clean these things up a little bit. There's like a binary opening operator you can do where you basically take a pixel and you clean up around it, basically. And when doing that, I sort of said, well, I always know that there's going to be RFI around this frequency band. There's always going to be RFI around here. So in those frequency bands, just maybe do more cleaning or be more particular about the cleaning. So that's how I dealt with RFI. Yeah. Cool.
All right. Thank you. Hannah?
Hi. For the labeling, did you think about maybe using active learning?
No,
yeah.
is the short answer. Do you mind elaborating on that?
Yeah, I haven't used the method myself, so I'm not sure about how applicable it is. But yeah, it's, if I remember correctly, a method to automatically label the data, but with a human in the loop. So yeah, I think you give it some training data, and then it learns to label the data. But if it sees an example where it's not sure of, it asks about it to the human in the loop, and then it learns further from that.
Yeah, okay, that's, yeah, I'll definitely look into that. That could be very, very useful, yeah. Thank you.
So instead of checking your Instagram, you can be saying yes, no. All right, thank you. Any more questions in the audience? I have a comment. So obviously your current setup is geared towards type 3s because you said your windows are 1 minute, right? So so anyway, you wouldn't be able to really teach the algorithm to catch type 2s, right? But what you could do is try to see if you could possibly remove the type 3-like features from the type 2s and just leave the large-scale features in the end. So I don't know if you want to comment on this.
Yeah, that's a good point. Like maybe there's a few more things like pre-processing steps that could go into highlighting large-scale stuff like type 2s, and then again coupled with having a larger input image. I think that would better capture some stuff. Definitely worth looking into though.
All right, thank you. Any more questions here from the audience? Any questions online?
I don't see any other questions, but I have questions myself.
Yes.
Questions myself, if I can. Hey, Pearse.
Hi, Pietro.
Stuff. I think it's great. We should definitely chat about how to try this also on the LoFAR data. Mattia Mancini is there, and he will present tomorrow. And in fact, maybe you guys should chat. He will present something similar that we're doing with the LoFAR data. So I was wondering if you are also in need of a sort of a data set which is labeled. We're actually have labeled if we have some training data set of about 3,000 now, 3,000 images. But we're planning to put them into this project called Zoo Universe, and let the people classify them for us. So maybe you guys should maybe chat.
Yeah, definitely.
Your talks are not together because they were similar, but yeah.
Okay, cool. Thanks for that. Yeah, I'll definitely chat. Yeah, brilliant.
Thank you, Pietro. Any last questions? There are no questions online. Let's thank the speaker one more time.
Thank you.